Swayam Prabha. Digital India. Educated India.
Going through the single physics models are to have an understanding of how each model is set up, whether it's a partial differential or an ordinary differential based upon we are doing a steady state analysis or a transient analysis. And our understanding of the models help us to create a link between the two models, and after today's lecture, which is the last for this segment on the single physics system, we will move on to multiphysics modeling and multiphysics equations. Okay, so in today's lecture we will cover the concepts of electrochemistry. We have been covering most of the concepts of physics. Heat and mass transfers are the fundamentals for transport phenomena in any mechanical or a chemical system. Solid mechanics is an essential part for mechanical, aerospace, civil engineering. At the same time, fluid mechanics is useful in mechanical engineering, in aerospace engineering, and in the other divisions as well. Likewise, electromagnetism is getting to play an important role now in many of these engineering applications, wherein we are trying to use the effects of magnetic fields and the electric field induced magnetic fields on different materials and seeing how their material behavior, like their stress strain relations, vary. Right. Electrochemistry is the last binding segment. We are moving into a world of green energy, and electrochemistry is an important segment in that. That is, the most common terms we see nowadays are batteries or lithium-ion batteries. So, this is a cell representation of a battery and a fuel cell. Two are the two pillars of electrochemistry and for energy storage when we are looking for electrical energy storage. Right. So, when we see solar cells or hydroelectric plants, or we look at some of the renewable energy sources, the major challenge we face in those is that the source of energy is intermittent or is not continuous, which means that during the daytime sunlight is there, but if it is cloudy or during the night, then we do not have sunlight, which will lead to an absence of the production of electricity. So, but during production we might have an excess of what we need. That excess energy can be stored as an electrical energy. This electrical energy is converted to a chemical form, and that chemical form is later on converted back to electrical energy, and that is the work of a battery. Right. Likewise, when we are running vehicles, instead of burning fuels like petrol or diesel and using that to move a crankshaft, to move a piston and a crankshaft that will provide power to the wheels, we can charge our battery at home. So, electrical energy is converted to chemical energy, and then during operation that chemical energy is reverted back to electrical energy, which is used to drive an electric motor. Electric motor follows the principles of your electromagnetism. It is an essential part of electrical engineering and coming in the other fields, and therefore, we are using chemical energy which was stored in the battery to generate electrical work output, and that work output is then used to run or operate a vehicle. So, that is a part of electric vehicles. Since green energy and energy technologies are gaining so much importance, so are these battery technologies, which were earlier we were only relying upon lead acid batteries, which were the older concepts. But nowadays lithium-ion batteries have become prevalent, and we are gradually moving on to the concepts of fuel cells. Okay, so let us first talk about batteries, and then we will go into fuel cells. So, battery is something which works between your electrical energy and your chemical energy. So, chemical reactions or processes, they store energy within themselves in the form of potential. That is, during chemical reaction, when an ion converts from one state to another, or an element converts from one ionic state to another ionic state, in that case there is a potential difference created. This potential difference can when connected through a conductive pathway, can cause electrons to move, or can make the electrons move. We have already talked about electromotive forces in the last lectures on electromagnetism. So that voltage difference is your source energy, your source potential, and that is causing the electrons to move through an external circuit. Right. So, we can use electrical energy to convert and store as chemical energy in the form of a chemical reaction, and that reversible reaction can be converted back and giving out electricity. Okay, that is a work of a battery. So, in a battery we have two electrodes. These are called electrodes. We have a cathode and an anode. Our cathode is positive and our anode is negative. Right. So, this is our positive electrode and this is our negative electrode, and the two electrodes are separated by a separating membrane, which does not allow electrical transport between the two solutions. Means we do not allow internal transfer of electrons, we only allow the electrons to flow through the external circuit. Internally only the ions are allowed to move, and that is the work of a salt bridge or an electrolyte bridge. So, it is called separator or electrolyte bridge. Right. And so a battery, your negative electrode will give electrons, a positive electrode will accept electrons, and in this process electricity is transferred. Electrons go from the external circuit, ions will go from the internal circuit. So, we are getting a sense that there is some sort of a transfer. We have modeled of ions or species through mass transfer. So, we will definitely be using mass transfer equations. Electrical energy or electrons are flowing means it should satisfy some form of kinetics or some form of current voltage relation. It could be Ohm's law under certain materials, it could be some other experimental based relation. So, we are getting a sense of electrodynamics from this case, right. At the same time, we also have some thermodynamic potential that is driving them. So, it relies on thermodynamics. Therefore, we can see that the battery itself is a multiphysics problem. We are concerned with charge conservation, mass conservation. At the same time, we are also concerned with the Ohm's law or a current voltage relationship. So, we are now gradually moving away from the single physics and entering into or starting to enter into a domain of multiphysics systems. Okay. On the other hand, fuel cells are slightly different from a battery. So, fuel cells, it will convert a chemical energy of a fuel directly into electrical energy without any intermediate pathway, right. So, a typical energy conversion route is that you combust a fuel that generates heat, you use that heat to drive a turbine through some mechanism, and the turbine would then connect it to an electrical generator, would generate electricity. In this case, it is generated directly. Your fuel is oxidized, and by oxidation it releases electrons. Those electrons travel to the external circuit and creates a potential difference. That is what operates the external circuit. So, your fuel cell or a fuel battery or a stack of fuel cells together, you can directly convert a fuel combustion. It can be any fuel, it can be a hydrogen fuel cell, it can be a methane fuel cell, any kind of fuel cells. You can directly oxidize the fuel. So, hydrogen converts to water, methane may convert to carbon dioxide and water, and so on. And electricity you can get will be of high conversion efficiency in contrast to a mechanical process in which turbines are rotated and electricity is generated through generators. Okay. So, therefore, the study of electrochemistry and in overall electrochemical systems becomes important as it does interact with other physical systems. Say an electric vehicle has an electric motor connected to a battery. So, you need to understand the working of a battery or electrochemical system. At the same time, you need to have an understanding of how electric motors or an electromagnetic system works, and that is where we are having an interface between two physics. Okay. So, the electrochemical cell, the first practical electrochemical cell was found by Alexander Volta. In the year of 1800, right. So, this was called the Volta pile. So, Volta was doing some experiments in his lab, in which he, like many of the experiments and many of the discoveries are serendipitous. He had some tarnished silver, and this is a pictorial representation of the Volta pile on the right. So, he had some tarnished silver sheets with him, and he also had some zinc plates, right. So, what he did, he took some of his filter paper or some paper material, and he started sandwiching his silver and his zinc together. So, it was a zinc 2 plus and a silver plus silver system. So, tarnished silver is that it is a silver sheet where the surface has been corroded and it is forming silver oxide. Right. What he put in the center as an electrolyte, he added some drops of potassium hydroxide, and 1 molar solution of potassium hydroxide, and he found that a potential difference is created between the two terminals. One terminal is your zinc and one terminal is your silver. Right. So, something happened. As soon as you added your potassium hydroxide and you have this sandwich, there is a voltage difference and electricity or a current started to flow between them. And it worked up to a certain point at which the potential difference became 0 and the current stopped to flow. Okay, so, what he came to realize is that some chemical reaction is happening. One reaction process, that is a zinc plus, is at a different voltage scale than the other reaction, that is silver plus. Right. So, he deduced that zinc is going into zinc 2 plus and giving out 2 electrons, and silver is accepting those 2 electrons, the silver ion, and is going into the silver metallic state. And this is the process that is going on in the battery. What is an anion in this case? An anion is the potassium hydroxide or the KOH. Right. So, in this case, the electrolyte which is providing the anion was KOH, potassium hydroxide, right, and that is giving you OH minus. This OH minus would travel between from silver to zinc, and OH minus will go through the separator, and the electrons will go through the external circuit. This is the net reaction that happened in the Volta pile. So, this is the Volta pile reaction. We can see, so this is the overall reaction. So, we can see that what is giving electrons is your negative terminal. So, at the negative terminal, zinc is getting oxidized to form zinc 2 plus. So, the zinc is going from 0 state to 2 plus state and giving out 2 electrons. The silver is getting reduced by accepting those 2 electrons at the positive terminal, and it is going from plus 1 to 0 state. Okay, so, this plus 2. So, this is a net reaction that is happening in the Volta pile. Now, this circuit that is being driven, it depends upon many parameters. It is not as simple as it looks, that there is a chemical reaction creating a voltage and causing the electrons to transfer, that is fine. But in the process, where is the chemical reaction happening? It is happening at the surface of the electrode. Right, the bulk of the electrode is not involved in the reaction process. It is a solid metal. Only the surface of the zinc is getting corroded and is forming zinc hydroxide. Only the surface of the silver oxide is getting reduced to form silver. Right. So, it is a surface interfacial process rather than a bulk process. So, several factors or parameters affect or the driving forces. So, the driving force for the reaction is determined by the thermodynamics. Properties of the electrodes, right. But that is just a driving force, but what is causing the reaction to move is the rate of the reaction, is driven by the interfacial kinetics, and depends on mass transfer and reaction rates. So, at the electrode interface you will have a chemical reaction and therefore, some chemical kinetics. Then the hydroxide ion, it needs to transport from the silver to the zinc, and that means that there is a mass transfer occurring due to a concentration gradient, right. So, overall all of this together is what makes up a battery. So, we can see in essence that this becomes a multiphysics problems in which different physical phenomena are interacting with each other. Okay, we will start with some definitions. So, the first definition is there are two types of electrochemical systems. The first is called a galvanic cell. Right. So, this derives energy from spontaneous chemical reaction that produces an electric current. In the external circuit. Okay, so, typical battery, when you connect the two terminals and the electrons are flowing through the external circuit, or you have power at the outlet, that is in very common term, that is called a galvanic cell. So, your electrodes are at a state in which they want to undergo a spontaneous chemical reaction, but due to the lack of an external path for electrons to flow, they are unable to do so, and such a cell is called a galvanic cell. The opposite of this is called an electrolytic cell. Right. So, this is the reverse of a galvanic cell. And it needs energy for the reaction to occur. Right. So, that means that now the battery is fully discharged, there is no potential difference between the two electrodes. Now, you need to connect a power supply to the battery when your battery is fully discharged, and it reverses the process to bring back everything to the original state, that is fully charged state, that is called an electrolytic cell. So, a battery can be both a galvanic cell and electrolytic cell based upon which direction of the reaction you are moving. If you are going from zinc to zinc 2 plus and silver plus to silver, then it is a galvanic cell. If you are going from silver to silver plus and zinc 2 plus to zinc in the reverse direction, then it is an electrolytic cell. That makes sense? Yes. Now, we will consider the parts or components of a battery. The types of cells. So, components of a battery, you will have your electrode. So, electrode by definition is a material that allows electrons to be mobile or electrons to transport through. They are good conductors of electricity. Okay. So, it is they are materials electrons are mobile and can be used to control or sense the chemical reaction, the potential of the electrons. Right. So, they allow free mobility of electrons. So, zinc is an electrode, silver is an electrode, copper is an electrode, all of them allow free mobility of electrons through them, and you can measure the potential difference between the two because they are allowing electrons to transport through them. That is the sense of the potential of electrons, the potential difference, and that is electromotive force. Okay. So, they are typically metals. Can be metals, it can be alloys or intermetallics. They can be some transition metal compounds, metal systems. Can be semiconductors and so on. The second one are electrolytes. Okay, so they are typically solutions or materials. It can be solid as well, solid electrolytes, which allow ions to be mobile, but electrons to be non-conductive. Right. So, the ions are the mobile species and the electronic conductivity are very poor. So, these are materials. So, ions are mobile and electron movement is limited. Right. So, electron movement or electron motion is limited, ion motion is free. An example of it can be ionic conductors, molten salts, dissociated salt solutions, and some specialized ceramics. Right. So, these are the electrolytes. The third and the final component, that is component C, is your salt bridge. This allows ions to communicate between the two electrodes, the pathway for the electrolyte. Right. So, a salt bridge is something that allows the ions to flow through. It will absorb the electrolyte and it will connect the two electrodes, but will not allow electrons to transfer, only the ions can transfer between them. Okay. Now, we look at the concept of charge conservation. So, charge conservation is the fundamental for most of the chemical reactions. Most of the species are electroneutral. Electroneutrality means that your net positive ions equals the net negative ions, and the summation of the ions concentration charge into the concentration is equals to 0. So, most of the chemical reactions follow electroneutrality, which means that summation of I for I number of ions is 1 to n of Z I C I should be equals to 0, where Z I is the charge on ith species and C I is the concentration of ith species. Okay, so that is Z I into C I, where Z I is a charge. So, for example, zinc and silver, you will have 2 charge on one atom of zinc and 1 charge on 2 atom of silver. That will give you a net charge balance. Right. So, let us write it down again. So, you will have zinc going to zinc 2 plus, silver plus, 2 silver plus going to silver. Right. So, we will have 2 into CZN 2 plus, and in this case 2 electrons are being given out, in this case 2 electrons are taken, and then we will have minus. So, you can take minus for 1 and plus for 1. So, minus concentration of Ag plus, and this should be equals to 0, or we can say that zinc 2 plus concentration, well, rather 1 by 2, 2 of this. Let us write it again. Z for zinc 2 plus is 2. So, 2 for the concentration of zinc 2 plus, and then for the silver concentration it will be minus 1 charge. So, charge number is 1 for Ag is equals to 0. For every atom of zinc dissociated, it gives 2 electrons, right, and those 2 electrons needs to be absorbed by silver, right. So, CAG should be equals to 2 C zinc, that is the significance of this, right. So, if zinc is 1 molar, so you have 1 molar of zinc is getting consumed, then 2 molar of silver will also get consumed, right. So, zinc 1 molar of zinc is getting consumed to zinc 2 plus, 2 molar of silver plus is getting converted to silver. That makes sense, right. So, that is the net charge neutrality for the given system. Now, based upon this, we can say that the mass and charge can be related. So, the mass of species consumption is related to the charge transfer this is called the Faraday's law. This is not the Faraday's law of induction, this is the Faraday's law for electrochemistry or process, Faradaic law or Faradaic reaction or Faradaic process, which states, so this states that the amount of chemical reaction is proportional to the amount of electricity passed, and such a reaction is called a Faradaic reaction. Okay. Now, the total mass of the species Mi therefore, will be equals to minus Si, molar mass Mi, the current, the time t it has been passed, and the number of electrons transferred m into Faraday constant F. Okay. So, where Si is the stoichiometric constant coefficient of ith species, is the molar mass of the ith species, I is the current passed, T is the time, N is the number of electrons in the reaction, and F is the Faraday constant. Constant, right. So, from this equation we can find out the net mass of species consumed for the ith species being consumed. Now, since we have an understanding of what Faradaic process are, this is a comparison between a Faradaic process and a non-Faradaic process. So, if you look at the slides, we can see that the charge transfer process in the case of Faradaic reaction is directly proportional to the electrons, say zinc is going to zinc 2 plus. So, in that case we will say that, so let us write it down, zinc is going to zinc 2 plus and giving out 2 electrons. Then the mass of zinc consumed will be proportional to the current being transferred, right, into time, and that is what we wrote in the last slide. So, if 2 electrons are transferred, then 1 mole of zinc is consumed. If 6 electrons are transferred, then 3 mole of zinc are consumed, and if you know the molecular weight of zinc, we can find out the total mass of the species consumed or the rate of consumption of the reaction. So, it is direct proportionality, your current translates to the species amount or the species mass. On the other hand, if you look at non-Faradaic process, and the non-Faradaic process are the ones in which charge transfer is not direct, right. It is there is a charge storage mechanism, right. So, a non-Faradaic reaction, the electrode / solution interface will show a range of potentials under no charge transfer. Reaction. Okay, so such reactions are thermodynamically or kinetically driven, unfavorable. And occur due to surface adsorption and electrode modification. Okay, I will explain what I wrote. Alright, so a non-Faradic process, unlike a Faradic process that we have seen in the last slide, Faradic process, one electrode has one voltage. If zinc is going from zinc to zinc 2 plus, there is a certain voltage in the electrochemical spectrum or the electrochemical series, and that drives this Faradic process. In non-Faradic process, typically say you have a graphite electrode, say in a lithium battery, and lithium ions intercalating into the electrode. Right. So, the electrode's charge transfer is limited by this diffusion process. So, ions need to diffuse into the lattice, and that diffusion process is creating a new structure for the ion, and that is causing the voltage to gradually change. So, there is no fixed voltage, the voltage will change based upon the mass transfer process. So, most of the current day battery like lithium ion battery or zinc ion battery, the rechargeable batteries that we see which show or exhibit a voltage range, those are all non-Faradic process. Since they are non-Faradic means that their voltage will be a function of the state of charge, how much charge is there of the battery, and the state of charge is determined by the ion diffusion through the electrode. So, as the ions will diffuse or the atoms will diffuse into the structure, it will create a modification. The surface is modified, the electrode structure is modified, and that is what is causing the voltage to gradually change. It is not a step value, it is not one value, it is a gradual nonlinear function of the concentration of the ion diffusing into the structure. Right. So, these are some of the examples or to show how the Faradic process works, whether it is in ion or in a solid metal ion or in a gas anion. Non-Faradic process on the other hand, ion can be absorbed say in a carbon microporous structure. It can be absorbed in intercalation structure like I talked about in lithium batteries, where lithium intercalates into graphite or in the lithium cobalt oxide, and then the ions are absorbed in a surface modified carbon. So, you can have nanoparticles which can absorb the ions at the surface. These are all non-Faradic processes which do not follow Faraday's rule. I hope that understanding is clear about the different reactions. Now, thermodynamics of electrochemical reactions. I would expect you have a certain understanding of thermodynamics at this stage and would not like to revise your concepts of Gibbs free energy, enthalpy and entropy. We will start from the point that we know that delta G is equals to delta H minus T delta S, and this is the fundamental formula of Gibbs free energy. Gibbs free energy combines the first law with the second law. The second law, it gives the direction of change of entropy, that is delta S. First law gives you the enthalpy or the conservation of energy. Okay. From here, this we also know is equals to minus RT ln K. Okay, where K can be Kp in the case of gas, that is equilibrium potential, is a pressure based equilibrium constant, or Kc, which is the concentration based equilibrium constant. So, K is equilibrium constant. RT, where R is the gas constant, T is the temperature. Okay. Delta G is the Gibbs free energy. Now, what we see in an electrochemical system, this delta G is related to the electrochemical potential by the formula that delta G is equals to minus NF delta E, where delta E is the cell potential difference. We do not write absolute cell potentials in the same way we do not write absolute Gibbs free energy. It is always a relative term between two species or between two electrodes. Okay. So, delta G is equals to minus NF delta E, where delta E is a cell potential difference that will be E between the cathode minus E of the anode. Okay. Now, if some of you might wonder, now why did I not write delta E for cathode? It is actually delta E for cathode. When we measure for a full cell, we can also measure for half cell. Half cell means that the reference electrode is considered 0 and your measurement is against that reference electrode. So, you have say we have a hydrogen H2H plus system that is assumed 0 in the electrochemical series. If you measure your cathode potential against that, that will be your E cathode, and anode potential will be your E anode. Now, the difference of the two for a full cell will be E cathode minus E anode, and that is delta E for your battery. Right. So, again we are introduced the concepts of half cell and full cell. So, what is a half cell? So, half cell is an electrochemical system can be split into the redox part can be split into reduction at one electrode and oxidation at one electrode. So, your redox reaction can be split into reduction against a standard cell and oxidation against a standard cell. Okay, so, standard reference cell will be hydrogen H plus. There are other standard cells, silver plus. In the case of lithium battery, it is lithium metal. So, you can use any counter and you keep that reference as constant. So, that when you subtract the two, E cathode minus E anode, that reference term gets cancelled out. All right. So, if that is clear, then we can say that for an open circuit cell, of no activity or unit activity, delta G naught equals to minus NFE delta E naught. Okay, this is called the open circuit voltage. Now, what is an open circuit voltage? Is that if you have a cell connected to a resistance, right, and if this resistance tends to infinity, that means that your current is very small, there is a very small amount of current flowing that is not capable of showing a significant amount of work. In that case, the cell potential that you measure using a voltmeter across the battery is called your delta E naught, or your open is also given by UOCP. That is open circuit potential. The corresponding delta G will be delta G naught under the standard conditions. Okay. Now, let us see what is how the cell voltage or the electromotive force of a cell is related to concentration. We can take a general cell, consider a general cell. Right. So, your nu O into oxidizer plus number of electrons is nu R for the reduction reaction. This can be converted to a half cell, right. So, in this case we are giving the full cell oxidizer and reduction. Now, let us consider a half cell. We will take the hydrogen H2 for H2 plus nu O into oxidizer will go into nu R for the oxidized reduced products and nu H plus into H plus. Okay, so, this is a half cell, there is a half cell reaction, the half cell against hydrogen. Okay, so, we are doing it against hydrogen. Now, the delta G is equals to delta G naught plus RT ln K, and what is K for a chemical reaction? It is a ratio of the activity AR nu R AH plus, that is for the product of nu H plus divided by A for hydrogen nu hydrogen, A for the oxidizer material and nu O. Okay. This you should know what Kp or Kc is, what is equilibrium and concentration. It is a ratio of the concentration ratios. In this case, it is concentration ratio multiplied by a factor. That is what we will write. This is called the activity. So, where A is the activity, right, and A of I for an ith species is gamma I Ci minus C naught where C naught is the reference, typically 1 molar, Ci is the concentration of the ith species, and gamma I is the activity coefficient. If it is a gas, then Ai is equals to gamma I Pi over P naught, where P naught you can take as 1 atmosphere. Okay, so you take it against a reference. All right, that makes sense. Let us go back one time. So, we said in the last slide is that for a unit activity, delta G naught is equals to minus NF delta E naught, and if your activity is unit, that is equals to 1, then natural log of 1 is 0 and delta G will be equals to delta G naught. So, that makes sense what unit activity means. All right. Now, let us substitute delta G is equals to minus NF delta E. So, we will have minus NF delta E is equals to minus NF delta E naught plus RT natural log of let us name it K, or we can write down the terms AR nu R, AH plus nu H plus, AH2 nu H2, AO nu O. Okay. We can divide by minus NFE throughout, and delta E therefore is equals to delta E naught minus RT natural log. Activity for H plus and H2 is 1. That is the purpose of a standard reference cell, that the activity is 1, that is your half cell part, and therefore you can write AR nu R over A0 nu 0. This equation that you are getting is called the Nernst equation, right. This is your Nernst equation, and this is against your normal hydrogen electrode or NHE. Okay. Now, it is difficult to sometimes measure the activity. What you can do is you can take out, so the activity coefficient is difficult to measure. Right. So, what we can do is we can break this into two terms. So, delta E is equals to delta E naught minus RT natural log of gamma of R to the power of nu of R, then concentration of R to the power of nu of R, and divide by gamma of O to the power of nu of O, concentration ratio. So, you can put a C star or normalized concentration of O nu of O. Okay. We can separate this into two terms, one with respect to gamma and one with respect to concentration, and what we find is that we can measure everything with respect to concentration, and delta E naught prime is equals to delta E naught plus RT over NF over NF. I am forgetting this NF throughout, you have to divide by NF. So, RT over NF, we can put minus, but if you flip the signs, it will be plus natural log of your concentration for the O to the power of nu O over concentration of R star star normalized to the power of nu R. Okay, so I have just flipped the denominator numerator, that makes it plus, right, and this is your E naught star, and therefore, delta E will be equals to the delta E naught prime minus RT by NF natural log of gamma R nu R by gamma 0 by nu 0. So, you can find out this cell voltage from concentration, and then you can measure the difference from the measured and the open circuit, and that gives you the activity coefficient. Okay. All right, we can skip this slide. We will go on to the kinetics and the reaction rate. Now, what is reaction kinetics and reaction rate? Now, any chemical process that happens, say the zinc 2 plus and the silver plus silver, at the interface of the electrode, the current and the voltage needs to be related, right. Likewise, for a in this case Ohm's law can be very well used, but but in the case of non-Faradaic process, the reaction is not linear, or the current and voltage are not linearly equivalent to each other. There is a function, and that is called the reaction kinetics or the reaction rate. Right. So, so under an open circuit condition, the driving force of electrons is the over potential called eta S between the electrode or at the electrode. Okay. So, we are saying open circuit, but there is still a small amount of current that is flowing. It is not always not exactly 0. To drive that small amount of current through, an over potential is needed, or at the surface some charge accumulation is needed to push that current through, and that is your current voltage relation, where I is equals to I naught, it is some constant current, exchange current, exponential of alpha A f over R t into eta S minus exponential of minus alpha C f over R t eta S. Okay, then this is your exchange current density. It may depend upon concentration, it may depend upon any other factor. It is an experimentally measured value and something that is curve fitted. And this kinetic law is called the Butler-Volmer kinetic law. Kinetic model, not law, right. This part is your anodic driven, and this part is your cathodic driven. Right. So, this equation can also be split into two. I can be equals to I naught exponential of alpha A f over R t into eta S, if alpha A f eta S is greater than R t, and minus I naught exponential of minus alpha C f over R t into eta S, if this alpha C f into eta S is less than minus R t. Okay. This is called the Tafel kinetics. Okay, so, the kinetic model will depend upon the material or the reaction process, and whichever reaction we are using, based on it you may come up with the reaction kinetics. Okay. The last part of our talk will be going on towards the transport of species, or the species kinetics, species diffusion. So, the transport of species in an electrochemical process can be driven by three factors, the three driving forces. The first will be your concentration driven, the second will be your bulk flow, bulk motion, or this is called diffusion, or convection driven, and the third one will be due to an electric field. This is called electromigration. Okay. So, your ions need to move between the two electrodes, and the two electrodes are at a potential difference that is causing the ions to flow. So, there is an electric field, and that motion is called electromigration. And now, within the bulk, it is a porous media, and the electrodes and the ions need to diffuse through the porous media. If there is a circulation of ions, then its convection is there, otherwise it is driven by the concentration difference, that is called diffusion. So, these three we will talk in certain extent. So, diffusion, so we have already done mass transfer. So, you know the basic understanding of how a mass transfer equation is derived. We have this del C by del T equals to minus the divergence of the n, right, where n is the mass flux. So, for an ith species, there is the ith species mass flux. N is the parameter that we will be explaining in this case. If it is diffusion, right, then Nni for the diffusion is equals to minus di del Ci, and that comes from Fick's law, where d is the diffusivity of the species. If there are positive and negative ionic species, then d is equals to the ion number plus the participation or the mobility of the electrons, u plus d minus z minus u minus d plus u plus minus z minus u minus, right. So, diffusivity depends on both the positive ionic species and negative ionic species. For the most extent, you will only be using this Fick's law equation, and the diffusivity will be an experimentally determined quantity for your system. So, this is diffusion. You have a species, say this is your electrode, your ions are coming from all the way around, and there is some diffusivity through it. You have a mass flux at the surface, and that mass flux and diffusivity can be related. Second would be convection. Convection is due to the bulk motion. Okay. The Ni for convection is equals to Ci into V vector. So, you have a flow, you have a concentration, and that flow and concentration is what we will cause the ions to transport. In this case, it was minus d del Ci in the case of diffusion. In the case of convection, it is plus Ci into V vector. Okay. The current due to convection, or the current that is resultant from convection, is summation over I, or the ith species Zi Ci into Faraday constant into V. Let us see if that is correct. So, current is amperes in unit, that is coulomb per second. Velocity is meter per second. Faraday constant is coulomb per mole. Concentration is mole per meter square, and Z is dimensionless. The outcome that you will get is coulomb constant mole per meter cube. So, coulomb second meter square, that is amperes per meter square, and that is your current density. Okay. So, you have some flow, and due to this flow the ions are being transported, and that is called convection. The last is electromigration. So, in the case of electromigration, you have a potential difference, and that potential difference is causing the ions to flow. So, let us first see what is our Ohm's law. So, by Ohm's law, your current and is related to your potential. So, your electrolyte current, because we are talking about electrolytes in this case, right, it is mass transfer of the ions of the electrolytes, is equal to IE, where K is the ionic conductivity. Okay. The total current is equals to I equals to summation over I into Zi F Ni. That is what we have done in the last slide, where Ni was Cv. So, we have multiplied Cv, Zi F into Ni is a total ion being transported, right. Now, the velocity due to electromigration is Vi due to migration is equals to minus Zi into Ui. Again, Ui is ionic mobility, or the mobility of the species to go through, into the Faraday constant into del phi. Okay. So, phi E for the electrolytic potential. Okay. This is your velocity, and the formula is same as your convection, right. So, your Ni due to migration therefore will be equals to velocity due to migration, velocity vector, this is a gradient, right, the velocity vector due to migration for the ith species into Ci, it will be minus Zi Ui Ci. You can say u, some people write it mu, so you can also write it mu. If you are using mu, then let us change it in the diffusion term as well. These are all mu's. Again, these are mobilities. Zi mu I Ci into F into del phi E, and N is a vector. Now, the current associated, if we take this formula for the current, then I is equals to minus of F square. Now, there are positive ions and negative ions, we will account for both. So, Z plus square C plus into mu plus plus z minus square c minus into mu minus into del phi. This is your current density. And finally, you can put this current and compare it with this to find out the conductivity or the ionic conductivity. I am sorry, let us go back. Kappa is equals to this term plus f square z plus square c plus mu plus z minus square c minus mu minus. Okay, this is your ionic conductivity through the species. So, if you bring everything together, the total flux Ni total is equals to Ni due to diffusion plus Ni due to convection plus Ni due to electromigration. Okay, therefore, Ni total is equals to minus d del Ci plus Ci into V vector or Vi vector plus your plus electromigration term that is minus of Zi mu I Ci f into del phi. This is your total flux vector that you have. Now, you can put this into our diffusion equation and our diffusion equation is del C by del T, so minus del dot Ni total, and you will get your species conservation or species mass balance, right. From species mass balance and from your kinetic equation is finally what you can get your cell potential. So, your cell potential depends on, so it depends on your open circuit voltage, that is delta E naught. It depends on your over potential, that is eta S. It depends on your IR drops, that is your ohmic drop, how much across a resistance, how much voltage is dropped, and all of this together will give us that eta S for the anode equals to phi anode minus phi I, eta surface for the cathode is equals to phi cathode minus phi 2, okay, and then the voltage is equals to phi anode minus phi cathode, or the other way around, phi cathode minus phi anode, and we can plug everything together into this equation and we can find out what is the net cell voltage, right. So, this is mod of this is the cell voltage or the absolute of the cell voltage. This cell voltage is either need to drive an electrolytic cell, or it is a voltage that is given by a galvanic cell as a potential outcome, right. So, from electrochemistry we have now a sense at how thermodynamics gives the force to drive the system, how the mass transfer occurs and how the concentration changes, how concentration is related to the chemical kinetics, and from that we are getting the cell voltage of the battery. So, this is a multiphysics system. It is an introduction to see how different physics are starting to interact. From the next set of lectures we will go in full fledged into multiphysics modeling. So, thank you so much for listening today.
Hello and welcome to this piece of literary snippet. We usually know William Shakespeare as the most revered figure in the history of English literature. But we often tend to forget that he has also been one of the most hated figures in literature. And here I am not talking only about those boys and girls who have to memorize long sections from Macbeth or King Lear or Julius Caesar before they can go and sit for their school or college exams. But I am also talking about people who are themselves quite famous authors. Tolstoy, for instance, considered the writings of Shakespeare to be, and I quote, crude, immoral, vulgar and senseless. George Bernard Shaw absolutely loathed Shakespeare, as he did Homer. But perhaps no other criticism about Shakespeare is more damaging than the one which says that Shakespeare is a marvelous storyteller, provided someone has told him the story earlier. Now, this piece of criticism is particularly damaging because it is true. None of Shakespeare's plays contain any original story whatsoever. They are all written using pre-existing materials, pre-existing stories. Now, does that diminish the stature of Shakespeare as a dramatist? Well, I'll leave that for you to decide. See you in the next episode of Literary Snippets.